Can you share your screen?
Yes, I'm just trying to set up the slide. 1 second. So, okay, it is 10 now, so we can start. How many participants we have now? So, 266. Okay, so welcome everyone for the third lecture and the third day of the summer school. I hope you are having a good time listening to the lectures, and you find this series of lectures interesting. So this week we will have this same series of lectures and ending on Friday. Tomorrow is a holiday because of the Eid al-Fitr. And next week onwards, we'll have a slightly different emphasis, moving towards GR and cosmology. So this is the third lecture of the radiative processes. Now today's plan is the same as is given in the schedule. That is, Shomok's lecture on introduction to ANA would be at 11:30, and Dipanjan's lecture at 2:30. So we will start off with the lecture 3 right now. I think we have enough number of participants to start. Yes. So in the last two lectures, we learned about some of the basic principles by which we can model how emission from a given physical system can be modeled to travel across space and reach a particular point. So we learned about the radiative transfer equation, the differential equation that is used to solve for the evolution of the radiation and the intensity as a ray travels from one point to another point, and more emission is either added to that ray by various emission processes, or emission is taken away from that ray by absorption processes. Now today we'll start going a bit more deeper into understanding some of the fundamentals of these emission processes, and I will try to introduce the basics of how radiation is emitted by moving particles and how that affects the radiation that we see. And at the end of the lecture, I hope I'll have time, I'll start introducing one of the emission processes, that is synchrotron emission. So let us proceed. So till last time, and we had been learning about, say, different processes by which emission and absorption can be modeled, but we did not really talk about what is giving out this emission. So from a very basic quantum mechanical point of view, emission is just emission of photons. So the light or the electromagnetic radiation we see is just emission of photons. In a similar way, if an absorption takes place, that is, the emission or energy is taken out of a beam by a material, the absorption is nothing but, again, transitions of electrons from higher level to a lower level, so that it absorbs the incoming photon or interacts with it, and there is a downward transition. So there's the classical world where emission and as we observe is usually seen is linked very intricately to the quantum mechanical description of systems. So we'll slightly introduce these concepts here, just to give you a motivation of how these are linked. So first of all, let us consider a two-level system here, level 1 and level 2. Now suppose the system is excited to level 2. So this can be any sort of a system, an atomic system. For example, it can be the basic hydrogenic system with a proton and the electrons doing these transitions. Or it can even be an ionized system where it has a host of electrons as well as a central nucleus, but it's just one of the electrons that is causing these transitions. Or it can even be quantum mechanical, purely quantum mechanical spin flip transitions and something like that. So we are just generalizing everything into just describing a two-level system from a statistical point of view. So the first kind of emission that we often model is called the spontaneous emission. So suppose by some mechanism you have pumped the system to go from a lower energy level 1 to a higher energy level 2. So the system always has a finite lifetime of staying in that system, in the heightened or energized system, in an energized state at level 2, and it will make a downward transition. The lifetime of the system is given by this coefficient that is called the spontaneous emission coefficient, which is an A to 1. And I can see that this is in units of second inverse. Now, similarly, now you can try to understand that absorption processes can also be modeled in a similar way. So suppose you have the system initially lying in a lower energy state, which is state 1, and you have this this photon, which is demarcated by this graphic of a wave coming and interacting with this system at level 1. Now, this then will absorb this photon and make a transition to level 2. So from the point of view of the intensity in the beam, that photon is removed from the beam, and that is an absorption event. So what happens is you transfer the electromagnetic radiation into internal energy of the system by allowing the system to make an upward transition, an interaction. So from the quantum mechanical point of view, we treat this as saying that the total absorption coefficient would be related to some constant factor B12, and will be proportional to the intensity of the radiation that is coming here, which is obvious because then it would depend on the number density of photons that is incident on the atom. And this J bar is actually a slightly non-trivial definition. So it is the standard description of the solid angle average intensity, J nu, that I had introduced in a few lectures back. So J nu is nothing but you take a solid angle average of the intensity. But J bar is the fact that you integrate over the frequency, because intensity is a function of frequency. So it's energy per unit frequency. But for this case, as you can understand, this frequency is just this energy level. But that is not always the case, because there is a finite, so it's not just the energy at E1. There's a finite width along E1 that over which this transition will take place, over which this system lies. So the energy at the state 1 is not definite and discrete. And this is again coming from the basic quantum mechanical description of how particles are. So we always have a finite width associated with any energy level. And this is what this phi nu function gives, which is in other words called the line profile function. So as I said, J nu is the integral, and the line profile function is of course normalized so that it's almost like a deduct delta function. But it's not a pure delta function, it's similar to the delta function with a finite width. Delta function goes to infinity. So essentially, this is just semantics, but the absorption is proportional to the incident intensity, and this coefficient is called B12. But there is another very important factor here, which was actually introduced by Einstein himself. It is the stimulated emission. So stimulated emission is B21 J bar. So suppose the system has been excited by some means to level 2. It could be a photoionized, a photon-related excitation. For example, the incident photon comes and interacts with the system at state 1, puts it to state 2, or it could be collisionally excited. For example, two atoms are interacting and colliding with each other. One atom gives its kinetic energy to the other one. Sorry about that. It gives its kinetic energy to the other one, and this it makes it collisionally excited just by transfer of energy to collisions to go to the level 2. But once at level 2, it will have a tendency to decay to level 1 again. Firstly, due to the spontaneous emission, and secondly, due to the stimulated emission, which is the rate of decay from level 2 to level 1 is proportional to the intensity of the radiation at level 2 itself. And the photon is emitted in the same direction, and the photon is in the same state as a stimulant. So this is almost like a coherent emission as the emission that is corresponding to the state 2. So this is the same description as absorption, but this can be thought of as a negative absorption. So absorption is you take out photons from the energy from the incident beam. Stimulated emission is you add emission to the energy beam. So this is like negative absorption, and I'll come to that soon. So for thermodynamic equilibrium, when everything is in equilibrium, you should have that the total upward transition should equal the total downward transitions. So N1 B1 to J bar, which is the absorption, should equal the total emission, which is the spontaneous emission, which is N2 A21. So N2 is the number density of this atoms, let's say, in state 2. And N1 is the number density of atoms in state 1, and so on. So this is the spontaneous emission and then the stimulated emission. And just a little bit of roundabout things, you can clearly see that a system in thermal equilibrium, now remember that we already talked about black bodies. So this is exactly how a black body comes into play. The radiation is interacting with this atomic system, which is part of a material. And if the material is like a black body and the radiation is in thermal equilibrium with this material, then this is the form of the emission that we expect. Now, from our previous discussion, before I go to the previous discussion, from statistical mechanics, again, this is something maybe a bit advanced for some of you, so I'll not go into the details of it. If you understand this equation, good. If you do not, then just take my word for it. So in thermodynamic equilibrium, when a system has a steady state occupation number at different levels, it can be shown that the total occupation total number of atoms in a particular system is proportional to the exponential of the energy minus kT. So if you just take the ratios of the occupation number or the total number of particles in the different states, and this is also then multiplied by the degeneracy factors, which is something that comes again from quantum mechanical calculations. So then just taking the ratio of the exponential minus energy by kT, you get something like this, G1 by G2 exponential h nu by kT. Again, these are very fundamental things that you study in statistical mechanics. If people who have not encountered this lecture, this may seem a bit alien to you. But what this essentially shows is, so the N2, as you can see, before I go to that, what it essentially shows is that the probability of a system to lie in a given state with a given energy is exponential minus E by kT. Now, since this second state, the heightened state N2, is just one h nu not away from it. So the energy difference between these two states is h nu. So the total energy of the particles in this state is E, which is compared to which is a lower energy state, plus h nu, and that is why we get the ratio of exponential h nu by kT. Now, if we just put those in, so if I go back to my previous slides, you can see that there's an N1 by N2 factor here, which is the ratio of the number densities of atoms in state 1 and state 2. You can now use this expression to replace it here. And you can see that this expression is extremely similar to the expression of the black body radiation density. So if I go back to my expression of the black body radiation field, you can see this is what it is. So instead of these coefficients here, which is 2 nu square by CQ, H nu by etc., we do now express this in terms of these coefficients A21, B12, and B21. And then we already have these exponential factors. So this is, so J bar, remember, is the energy density. And so just comparing these two functions, we can relate these coefficients. These are called Einstein coefficients, and this is called Einstein relations. And all these Einstein coefficients are just related. So that's why the numerator and denominator, if you just compare with the Planck black body function, you can get these relations. So firstly, the term in front of the exponential should be 1 because there is nothing in there in the Einstein relations. And A21 by B21 is just 2 h nu cube by c squared. So from experimental verifications, if you can find one of the Einstein coefficients, you can find the rest. And why are these important? Because now we have a method by which we can relate the probability of emission from a particular system to get the emission coefficient directly. Why is that? Now let's say how you can derive the emission coefficient and relate it to the quantum mechanical properties. So just purely from the point of view of emission, it is just a spontaneous emission. So if you somehow take the system to level 2, it will decay back down. So this J nu that we have been using in the radiative transfer equations, that is nothing but the relation, is related to the A21, which is the Einstein coefficient. So if you have total number of atoms in state 2 as N2, or the total number density of atoms in state 2 is N2, then we know that once it makes a downward transition, it emits a photon with the energy of h nu naught. And since J nu is the energy emitted per unit solid angle, we divide by 4 pi. And since this is per unit volume, so we multiply by N2. And also we multiply by this profile function, because it is always the fact that the energy H difference between these two levels is not exactly h nu naught, but there is a finite width at the top levels as well, which is given by a Dirac delta function. So the emission coefficient for spontaneous emission is just like this. Now let us look at the absorption coefficient. Now let's say that an incident intensity beam is falling on this material. Then let's see the total energy that will be absorbed. Now, if there is n1 number of atoms at the lower state, so the total energy incident is the solid angle average quantity, which is the J nu. J nu, remember, is solid angle average. So we integrate over the frequency and over the line profile function, which gives a finite width, and average it over the solid angle. This gives you the J bar, which was there in my previous. Oh, sorry. Yeah, this gives you this quantity J bar, and J bar is J nu integrated over the line profile function, and J nu is solid angle average of I nu. So there's nothing new in here. This is what I'm doing. But this will then take away an energy of h nu naught. So the total amount of energy that is taken away from the beam is n1 times the volume times dt times h nu naught. So this is what you get. So if you just consider this as per unit frequency, then and per unit solid angle, then this is d omega by 4 pi. We do not perform this in these two integrals, and this is what we have. Now compare this to how we had defined the absorption coefficient. We had defined the absorption coefficient in a similar way, where we found that if the beam is traversing a length ds over an area dA, like a cylindrical structure, then the total volume is dA ds, and the total energy that was getting absorbed is I nu dA dt d omega d nu. So just to recapitulate, what we had was that fact that the total energy absorbed d I nu is alpha minus alpha mu I nu ds. So just simply comparing these two, we get a relation or an expression of the alpha nu, of the absorption coefficient, related to the quantum mechanical description of the system, which is given by the Einstein coefficient B12. And now it is making a transition h nu. So this is alpha nu at nu. So this is making an energy, absorbing an energy corresponding to h nu multiplied by the profile function. So this is your absorption coefficient. So now directly from just basic quantum mechanical principles, we can relate the emission and the absorption coefficients. Now remember, I had mentioned the stimulated emission is very similar to absorption, but in a negative sense. So instead of absorbing or taking away material, it's adding intensity to the beam. So for stimulated emission, we treat this as a negative absorption, because the logic, the flow of logic that by which we have derived this coefficient, that will be the same. because the stimulated emission is also proportional to the total amount of intensity that is falling, that is comparable to the atom at a particular energy state. So we treat this as a negative absorption. So the total absorption coefficient is given, can be described as N1B12, but minus N2B21. But remember, this alpha nu comes as a negative quantity in the radiative transfer equation itself. So this negative quantity given by the stimulated emission then becomes a positive quantity and adds to the emission in the actual equation of the radiative transfer. So this is how the expression of absorption coefficient looks like. But note here, there is something interesting inside the bracket. This is N1B12 minus N2B21. Now, we just learned previously that the B12 and B21 are related in this way, which is given by the Einstein relation that we find by comparing the Planck black body function with the effective expression of the energy density we derive in this way. So then, and also we know that N1 by N2 is related to the states and the exponential of h nu by kT. So we just use this and substitute here to get the final form of the absorption coefficient. And so first of all, well, this assumes a further approximation, which is called the local thermal equilibrium. So we can just take the N1B12 outside the bracket, which is 1 minus G1N2 by G2N1. And if it is in thermal equilibrium, as I had just explained here for thermodynamic equilibrium, the ratios of N1 by N2 is related to the exponential h nu by kT, which is what we have substituted here. So this is an important assumption, or in technical papers you'll also find this is mentioned. It's called LTE, or local thermal equilibrium. So in local thermal equilibrium, the local absorption coefficient is modeled in this way. So once you find the Einstein Bay coefficient, which is determined by experimental processes, or the emission coefficient, spontaneous emission coefficient actually, because they're all related. And then if you have an idea of the total number density at the state 1, you can find the total absorption coefficient. Now, we've been talking about emission since we're talking about quantum mechanical transitions and emission. So this is a good place to also introduce some basic concepts about emission lines, because if you remember in the first lecture itself, I had talked about the fact that the emission we see is either a continuum emission, which means the emission process occurs over a very wide range of wavelengths. And then there are emission line emissions, which is because of transitions between two levels, which is exactly what we have been studying right now. And when this transition takes place, the energy level is very, very finite in terms from the quantum mechanical point of view, which is related to the difference in the energies. Now, as you know, it's from the quantum mechanics, from the basic principles of quantum mechanics itself, the energy h nu naught is not exactly discrete. There is a small excursion about this energy. The first of it is due to the quantum mechanical nature of the transition, which is called the spontaneous decay rate, or the A21 coefficient. So actually, when you look at a spectrum, the total line profile would look in terms of the frequencies would look something like this, which is a Lorentzian function. So it is not a discrete function, because from the point of view of Dirac delta function, you can always construct a Dirac delta function such that if this gamma is very small, it will shoot up to omega equals to omega 1,2. Omega 1,2 is the frequency difference between these two transition levels. So this is nothing but a Lorentzian function, which is modeling almost like a Dirac delta function. The fact that since you have finite width over here, and that is why you don't have a pure Dirac delta function, but a Lorentzian function. So when you actually look at the spectral profile of the emission line, you will not have just a spike at omega 1,2, but a slightly broadened spike. But this broadening is extremely small, because the spontaneous decay rate is quite a small quantity. So the lines we observe, if it is coming from an extremely cooled down system, it will be extremely narrow line. And the only width would be due to the quantum mechanical broadening, which is quite small. But in astrophysics, that does not really happen. In astrophysics, as I had discussed, the region that is emitting will have a finite temperature. And if it is a finite temperature, then inside the system, the various atoms are moving about with respect to one another. And as they move about, the frequency at which they're emitting in the rest frame will be slightly different, will be the same, but the frequency that is observed by the observer will be slightly different due to the Doppler effect. Because as a emitting source is moving and emitting a radiation at the same time, the frequency perceived by an observer is different because of the Doppler relation. And so the Doppler relation is giving something by this. This is the expression of the frequency change. And so if it's moving with a velocity vz, just a example of a 1D system where it is the particles are moving in one direction for simplicity. The perceived frequency omega is related to the emitted frequency omega naught in this way. So essentially, as you can see, the difference in frequencies is related to the velocity of the particle. Now, the particle has higher velocity. The difference in frequency would be larger. Now, in a thermal system, we know that the particles are distributed according to a Maxwellian distribution. Now, again, this may not be very obvious to you if you have not done statistical physics, but since we are expecting that all of you are third year and onwards of BSc, most of you would understand this. There would be some who are from a technical background. You may find it a bit difficult, so I would urge you to learn more about statistical mechanics because these are fundamental points in physics. So a system in a thermal system in thermal equilibrium, the particles are defined by a Maxwellian distribution. So the probability of distribution of the particles is related to the exponential of the particle mass, essentially the energy divided by the kinetic energy by kT. Okay, but then just from this relation, we can, if we substitute the Doppler relation, you can get another relation like this, which is the probability distribution of the particles is related to the difference of the frequency and the mean frequency of the particles. And that is why, and now you can see that by this simple argument, you are starting to see that the total line profile of the probability distribution of the frequencies is starting to look like a Gaussian distribution. So if you normalize this, then this becomes a normalized Gaussian distribution. But the width is related to the temperature of the particles and divided by the mc squared. So then for a thermal system, from this very naive hand-wavy analysis, what you find is the fact that the width of the line that you'll observe is actually a Gaussian profile. Now, the next topic that I will talk about, I will not talk in detail, but this will be there in my notes. And if you want to follow it in more detail, you can follow it. But there is another level of broadening. I see one hand was raised, but I will come back to you after I finish a few slides. So far we saw there are two sources of broadening. One is the quantum mechanical broadening due to the finite lifetime of the particles in a given state. And one is a Doppler broadening due to thermal motions of particles inside the system. And that introduces a Gaussian distribution. And so in the frequencies. Now, there is another broadening, which is called the collisional broadening. What happens is, if you have particles that are emitting, for example, let's say a particle is emitting an electromagnetic wave. So the electric field of that electromagnetic wave would be given by this exponential I omega t, which is just a sinusoidal function. There will be a minus gamma t by 2. This is because of this finite lifetime of the particle. So this is not a continuous sinusoidal train, but a sinusoidal train with a decay factor, and given by the finite width. And then it will have a phase. Now, if this particle collides with another particle, the phase will change. So for no collision, if you just take a expectation or a mean of the electric wave of the electric field and average over the phases, it is 1 because it is autocorrelation. But if it is if the phases change due to collisions, due to random collisions, this total integral over time would be 0 because these two are not really correlated anymore. So from this, and this also comes from the basic point of a Poissonian probability distribution of the collisions. Now, if you do a little more involved mathematics, you can find that the mean of the Fourier transform of the electric field square can be expressed in this way, which turns out to be again a Lorentzian profile. So I will not go into the derivations of this because this involves some steps. This is best done on board work. It's not good to show this online. But I have left it here. You can also find the discussions here in the chapter 7 of Theoretical Astrophysics, volume 1 by Thanu Padmanabhan, if you feel more interested to look into it in more detail. But what is more important is not the mathematics of it, but the physical understanding of what is the expectation out of this. So after all this mathematical jugglery, what you will find is this the Fourier coefficient or the square of the Fourier coefficient is related to this complex integral, which can be again solved to find that it is again a Lorentzian factor. But the width of this Lorentzian factor is not just gamma by 2, which is the finite lifetime due to the quantum mechanical width, but it's also related to the collision frequency. So nu c is something that I did not discuss here, but it is related to the collision frequency over here, which is what is the time mean time between two collisions to take place. So if you have a high density, so you have a lot of atoms packed into a small volume, the collision frequency increases depending on the velocity of the particles. So this is how the collisional broadening occurs. If you have high density and particles are moving with some mean velocity, of course, the time frame between two collisions would be also smaller. And this is related to the velocity of the particle and the mean free path of the particles. So essentially what you need to remember is that the total width can be both a Gaussian distribution due to the thermal nature of the particles and Doppler shifts of the frequencies. But they can also be a purely Lorentzian profile if it is dominated by collisions and driven in this way. So in a realistic system, what we actually model this system is a mixture of both. So we model actual line profiles by something called a Voigt profile. It's spelled as VOIGT. The G is silent, and it looks something. So forget about this part for now. So it looks something like this, which these front factors are just normalization factors. But if you look at this integral here, forget the numerator. If it's just 1 by x minus u whole square by plus a squared, this is a Lorentzian function. And this represents the Lorentzian nature of the line broadening due to collisions as well as the quantum mechanical transitions. The quantum mechanical, the width due to quantum mechanical transition is extremely small, so it's mostly neglected. It's mostly the collisional width that contributes here, and it depends on the density. But if the density is low and the conditional terms are not really affecting things, then you have the standard exponential minus x squared, which is the Gaussian profile. So this is almost like a convolution between the Gaussian as well as the Lorentzian profile. And this is the fitting function that we use to model lines in actual astrophysical system. In most of the cases we deal with, they have low densities, so we can we just model them by a Gaussian system. But in many of the cases, we cannot do that. And the line profile really looks a bit asymmetric. It's not a purely Gaussian or a purely Lorentzian profile, and that is why we use a Voigt profile to do this. So before I go to the next series, let me see, there are a couple of hands. I can take 2 or 3 questions now. So Vikrant Sharma, unmute yourself and ask a question, please.
Good morning, sir.
Good morning.
Sir, can you please go back to the the slide where we have discussed about the Maxwellian distribution?
Yes.
This one. So why we have not considered the velocity square term in the Maxwellian distribution?
It is there, no?
So no, not in the exponential actually. The v square, like we have studied in thermodynamics.
Okay. No, so that is taken out in when you actually. So this is a 1D Maxwellian distribution. That term comes when you do a 3D Maxwellian distribution. What we are doing here, since this is one line of sight, we are just considering a 1D Maxwellian distribution. Okay.
Thank you, sir.
Good question. Okay. Next is Keshav.
Good morning, sir.
Good morning.
I have a question. Sir, as you have explained that if there is a star, the material in that star will emit the radiation, and the spectrum that we will obtain, there will be some width in that line that may be due to thermal and Heisenberg uncertainty principle. We will get Lorentzian or Gaussian curve. Suppose there is a star and it is emitting the radiation of Fe line. Now the star itself is moving away from us, and due to this there will be a change in wavelength, and what we get is now due to this what we get is the spectrum of increased wavelength. And suppose that increased wavelength fall on the another element like cobalt. Now how we will get that this wavelength is what we get is not of cobalt but of iron. So I think you understand.
Yeah, good question actually. So let me clarify a few things. Firstly, if the star itself is moving, let's not talk about the star. Let's talk about the emitting source because it's easier to talk in a generalized way. So if the emitting source itself is moving, the entire broadened line, they will have a total bulk shift in the wavelength space. Okay, so it will not be that the motion of the star will cause another broadening. No, the line profile will remain same. So if from the frame of the star, the line profile will remain same. But now if you go to a different frame with respect to which the emitting source is moving, the total say line profile has shifted. And this is more important because suppose we are observing distant galaxies at different redshifts, and all this there is a redshift dependence of the wavelength as well. You learn that in your cosmology course. So all these emission line profiles we see, they get shifted. So a very important example of this is suppose we are observing, say, the star formation from a galaxy. Now, in nearby galaxies or close to us, the star formation peaks in the range of the UV emission. So young stars, I mean. But if you go to higher redshift, which are very distant and far away from us, due to this cosmological redshift, the frequency at which we will observe them has a bulk shift towards infrared. And that is why the latest space telescopes being launched by NASA, this is called the JWST, the main frequency ranges are in infrared. Although the main science topic is understanding the native star formation, which is happening in the UV band. So in a similar way, the total shift of the bulk velocity of the emitting source will just shift the spectrum. Now, sorry, what was the other point? I sort of forgot the other point. Who was this? Was it Vikrant? No. I hope I had answered the question. You had something else, but I don't seem to recall what was the other point of it. So you are saying that if there's mixing of spectrum. Yeah, Keshav, yes, I recall the mixing part. So there will be a problem mixing if suppose there are two sources very close to each other, and then emission from one overlaps with the emission from the other. So there will be mixing. We can't really help that. But in most of the cases, if the emitting source the space outside looks crowded from here, but actually if you resolve and close things together, they are not. So in most of the cases, if you're observing an emitting source, you don't really have too much of other emitting features around it. But there can be blending of different emitting sources and have a complex emission profile. In that case, as I had mentioned in my lectures earlier, you need to model them separately using separate components, then separate out the components statistically to see if they're statistically significant, and then make the inferences. Okay, I'll take a last question. SM Rafi Adnan.
Yes, am I audible, sir?
Yes.
Good morning, sir. So my question was, would you please explain the mathematics and physics of void profile? Because I once tried to fit the emission profile to the spectra near the AGN, and it came out to be a void profile as the chi-square value was the lowest. So what is the physics behind it? Please, would you
Physics,
explain?
this is what I was talking about. This is the physics. I will not explain the mathematics of void profile because this is beyond my 4-lecture course that I have. I would need more time for this. I would ask you to look up more references for this. But the physics is what I wanted to sort of emulate here. It is the fact that the void profile is almost like a convolution between a Gaussian profile and a Lorentzian profile. Now, if you go back to the expression of the void profile, sorry, this is the expression of the void profile. So as you can see, this is what I'm doing is actually a convolution of a Lorentzian profile, which is phi L, and a 1D Maxwellian or a Gaussian profile. Now, if you normalize this everything in terms of this x, which is the ratio of the frequency with respect to the base frequency, then what you end up with this is this normalized Gaussian in terms of this this function u, which is omega minus omega naught by omega naught, and then the added function of the Lorentzian profile. So if the Lorentzian width is small, then you can completely neglect this quantity because this is almost 10 to 1. So it almost becomes just a Gaussian profile. But if the Lorentzian width is quite significant, that you have to include this factor, then you have to include the Gaussian profile. Another way of understanding is take the Lorentzian profile, and as you know, the Lorentzian profile can also be approximated as a Dirac delta function. So if you just have a pure Dirac delta function, this omega minus omega naught, this is then substituted into the Maxwellian function, which is a function of the velocity z, and you get a remnant profile that just looks like a Gaussian profile at the particular frequency. So void profile is nothing but a convolution of both these two processes. One, the Doppler-driven width, which is a Gaussian profile or thermal width, and two, the Lorentzian width due to a collisional width. We call the other one, the other Lorentzian, a natural width, which is related to the spontaneous transition, but that is very small. So the Lorentzian, collisional Lorentzian plus Gaussian thermal, these two mix together to give you a convolution, which gives you a void profile. Now, you should learn more about the mathematical definition of convolution and the properties of that, and that will give you some idea about what the void profile is. So I'll stop taking questions now. Keep your hand raised or keep your questions noted, and I'll come back to you at the end of the lecture. So in the next few slides, I will go a bit fast because I'm already running out of time, and I had hoped to cover a bit more than what I have managed to do. So this is just a definition of the introductions of Maxwell's equation. I do not need to introduce the Maxwell's equations to you. The only reason why I'm stating this is because I wanted to introduce what is called the Poynting flux. So from the basic formalism of electromagnetic radiation, you would know that there is something called the Poynting vector, which gives you the energy equation of the electromagnetic radiation. So if you have currents, so the energy equation of the electromagnetic radiation looks like this. So this is the energy density of the electromagnetic radiation. If for now, let us forget that there are currents. It's just the total electromagnetic radiation that is passing through space. So J is 0. So then rate of change of this energy is related to the flux of this quantity. And this flux of this quantity is the divergence of a flux. So this is called the Poynting flux. And this is the energy density of the radiation field. And so when we actually try to model emission from different emitting sources, what we try to find out is the Poynting flux and what is the energy density from the due to the particular emission mechanism. And just a property of electromagnetic waves in the CGS units, if you just take the wave equation and substitute this solution of the wave equation, you will find that the magnitude of the electric field and the magnetic field are same in the CGS unit. This is very important quantity to remember, because when we actually model emission from different sources, for example, say an electron is moving in a accelerated way in a curved path, we can compute its electric field. We can also compute the magnetic field that this acceleration would produce, and the total energy density has to be related in this way. But in CGS, if you just find one, you can find the other. It's very simple. And so this is the mean energy. So if your the electromagnetic wave is varying as a sinusoidal, also these are very a recap of what you must have studied in your courses. Then the time averaged Poynting flux can be written like this: it's a C by 8 pi, which is C by 8 pi mod E square or mod B square, as E and B are the same. And the time averaged energy density of the electromagnetic field is again U, or mean average U is 1 by 8 pi E square. Now, what is the reason I'm talking about all of this is, now look at the fact that the Poynting flux or the energy density can be trivially obtained if you can find the magnitude of the electric field or the magnetic field, any one of them. Now, if we find from due to some emission mechanism what the electric field would be, we can immediately find what the Poynting flux or the energy density is. And interestingly, this is expected. The Poynting flux divided by the energy density is just the speed of light. You can see from here. This means that Poynting flux is nothing but a flux of energy due to the electromagnetic wave. It would be very weird if it is not the speed of light, because the electromagnetic wave itself is moving at the speed of light. So this was just a reminder of what you might have studied and what we would need in the coming few lectures. Now, this is what is important now. I will not talk about the derivation of this, but the fields of moving charges are given by this time varying quantities in the retarded frame. So these are obtained by calculating the retarded potential. If you have not studied them, you will most likely go over them in your lectures in masters. If not, then you can look up the book by J.D. Jackson, which I had already mentioned, and then you'll find detailed derivation of this. I will only discuss the physical implications of these quantities. So it can be shown that if you have a charge that is in motion, the electric field of that charge looks something like this. And anything within the bracket RET called retarded means that the quantities or the distances, everything that is inside the bracket should be considered at a point at a retarded time, which is if your observing position is over here, then the retarded time is, or the TR is given such that it would the time taken by a photon emitted from here to reach the observing point. Okay, so this is the retarded distance. So at your actual time of observation, the charge might have reached here, but you will only see what the charge was doing at an earlier time, and that is defined by the path length and the time taken by the light to travel from this point to you. So that is why it is called a retarded time. These are all more advanced concepts. You will learn more in your masters, if not later. But what is important to understand here is the nature of these terms. So the first term of the retarded electric field varies as 1 by r square. So for now, let us forget about this. Let us consider the fact that the charge is in constant motion. So there is no acceleration at first. So the electric field at that time looks as 1 by r square. Now, if the velocity of the charge itself was 0, then you could have dropped this term, and this is exactly Coulomb's law. Now, the fact that the velocity of charge is not 0, you have this added factor here. So if you just look at the field lines, so forget the inner region for now. The outer field lines would look something like this. They will point to the current location of the charge. This is a bit counterintuitive, but the field lines will always be radially going outwards from the current location of the charge, which would be x equals to 1. Now, suppose at a particular time, the charge has decelerated. So the charge had started to decelerate, and it has come over here. So when the charge has stopped its motion, then it is, of course, the normal electrostatic field, which would be radial. But just earlier, as you know, the charge is the electric field was looking like this because of this relative motion of the charge. Now, the net effect of the charge decelerating and stopping is given by this term over here. So you can see this term has a term that is the derivative of the velocity, which is the acceleration. And these are all computed in the retarded frame. So this actual calculations are quite involved, actually. So there are two things to note here. First of all, the electric field is proportional to the acceleration vector, and it is inversely proportional to the distance. Now here, the electric field is inversely proportional to the square of the distance. So and here, the electric field is inversely proportional to distance. Now, if you look at the Poynting flux earlier, if you look at the Poynting flux earlier, the Poynting flux is related to the square of the magnitude of the electric field. Now, if you take a square of the magnitude of the electric field, just this term will give you 1 by r to the power 4. Now, if you consider this fact that the charge has decelerated, so between these two field lines, there is this thin layer of transition where the electric field is changing from its initial sort of configuration to the current configuration. And this change in electric field will be communicated to infinity. And this is exactly the electromagnetic radiation that is being emitted due to the fact that the charge has stopped. So this is a very nice illustration and figure in this book by Ribicki, and I will ask you to read it if you can. I'm just describing it in a very rushed detail because I don't have time to delve into all of this. But what is interesting is the initial configuration of the moving charge was looking like this. The final configuration after the charge has stopped is just purely radial, coming from x equals 0. And then there is a thin transition region over which this is changing. And this is the electromagnetic radiation that is spreading out radially, spherically outwards. Now, we all know that the electromagnetic radiation is carrying some energy or flux along with it. Now, at any given surface, if you take the total surface, if it's all spherically symmetric as this is, then you will multiply the total energy being transported as 4 pi r squared. Now, if you multiply 4 pi r squared to square of E square here, the first term has a 1 by r squared dependence. So the energy transported due to any change in over here will rapidly decay with time, decay with distance. However, for this term, it is a 1 by r squared dependence. So there is a r squared that comes from the area that cancels with the r squared in the denominator, and you have a finite term that is left here. So this is the energy of the electromagnetic wave, and we are very fortunate that our laws of physics are designed in this way, such that the energy of the electromagnetic wave is transported without decay to infinity. So this is what I really wanted to mention here. And going forward, what one can try to do is, for any given system, we can try to find out that due to the motion of the charges, what is the change in the electric field. Now, once we find the change in the electric field and relate it to the acceleration of the charges, we can immediately find what the what the Poynting flux would be. Once we find the Poynting flux, we can actually find the emission coefficient. So this is how all of this is related to the topic of radiative transfer. Now let's see what is there in the next. I will talk about this slide at least for today. Now, what is the total power radiated by this process? Now, for non-relativistic systems, we can actually drop this beta. Beta is the velocity divided by speed of light. So for non-relativistic system, we can drop this term here. and we have a final formulation of the electric field of the radiation component of it, and which is R cross beta dot, and the magnetic field is just R cross E radiation. So as I said, the Poynting flux can be trivially calculated if you just find the square of this magnitude of the electric field, and you can show that this is the magnitude of the electric field is related to the acceleration quantity u dot and the theta. Theta is if your acceleration is taking place in this direction, and what is your what is your line of sight or the line of observation, which is given by this r cap. So what you end up is with the fact is the fact that the total power radiated is given by the total energy transported by the Poynting flux. So power per unit solid angle, which is the solid angle is related to the total area as dA r squared d omega. So it's a small portion of area, and the solid angle that is substance is r squared d omega. So the total power, so this is the per unit solid angle can be related to in this way. So what is important is I'll come to the Larmor's formula, but what's important is the solid angle distribution of the power, which comes from this, just following the argument of the Poynting flux. Poynting flux is total energy carried per unit area. So then the total energy carried per unit solid angle is this. So you can see that there is a sine squared theta term here. And this sine squared theta dependence of the power is called a dipole radiation. So you can see that if your acceleration vector is here and if your line of sight coincides with the acceleration vector, you will not see any power. You will see the maximum power if your line of sight is perpendicular to the acceleration vector, which is this. And the total pattern of this, the sine squared theta looks something like this. So this is the total magnitude. So this pattern traces the total magnitude of the dp d omega over here. And this is called the dipole pattern. And I will just come to this maybe in 2 more slides. And this quantity integrated over the solid angle is proportional to the square of the acceleration vector. And this is called the Larmor's formula. Now, Larmor's formula is very fundamental and very, very useful in identifying the total power that is emitted, because now you can understand if you can find the total power that is emitted per unit solid angle, this gives us a direct relation to the J nu quantity for a particular given system. Because J nu is nothing but the total power, in energy per unit solid angle per unit second per unit frequency. So in any of the radiative processes that I will discuss in the tomorrow, what we really aim for is finding out this total power per unit solid angle and then finding the Larmor's formula. Just 2 quick things that I wanted to introduce before I end for today. I still have 2 minutes. Is the fact that in some of these emission mechanisms, what becomes important is the fact that the charges can move at relativistic speeds. So I just wanted to review some of the basics of relativistic transformation. So this is the the standard Lorentz transformation. So this is a lab frame and this is a moving frame. And if your particle is moving in this frame at an angle theta prime, then we can always define the angle transformation. So this is what is very important. That is why I wanted to come here. So if your angle that is theta prime in the moving frame, it is related to the angle in the static frame or the lab frame in this way. Now for highly relativistic speeds, if your beta is extremely large, you can show that for theta prime equals to pi by 2, then sine theta is 1 by gamma. Which so this is so it's always often quoted that your angle in the lab frame for relativistic motions goes as 1 by gamma. And this is just nothing but you take this angle transformations from basic special theory of relativity. And for theta prime equals to pi by 2, theta prime is the angle in the moving frame. Your angle in the lab frame is 1 by gamma. Now, what does this mean? Suppose in the frame of motion of the particle, or on the rest frame of the particle is emitting some emission, some radiation. And that emission is isotropic in the rest frame of the particle. So from the point of view of the particle, this is the rest frame of the particle, you have uniform distribution over all angles, and that is why you have a sphere. Okay, now you make this relativistic transformation to the lab frame. So as I just showed here, due to the angle transformations, this at theta prime equals to pi by 2, which is this blue line here, those lines will become 1 by gamma in the at an angle of 1 by gamma in the lab frame. So if the gamma is very large, say 100, for example, we can have Lorentz factors of 100 or more for some systems. So your angle becomes just a very small, tiny patch. So all of the radiation in the particle's rest frame that was concentrated between minus pi by 2 and plus pi by 2, they all get squished into a forward direction. It does not mean there is no radiation here, but the radiation density over here is extremely small. And this is called beaming of radiation. So for example, if the particle is moving and emitting radiation, all of that radiation in the lab frame or the static frame is beamed along the direction of the particle. So the radiation in the lab frame becomes strongly anisotropic and beamed towards the forward direction of the particle. And this has important implications. So again, I do not have time to discuss in more detail about all of these equations that are quoted here. These are there from the Ribicki Enlightenment. But what this shows is the total dp d omega and how it is related to the dp d omega in the rest frame. So the angular distribution of power calculated in the rest frame of the particle looks like this, which is the standard expression of the Larmor's formula I just discussed a few slides back. Now, if you follow some basic principles of relativistic transformations, you can show that the power received by an observer in the lab frame would look like this, where these A perpendicular and A parallel are components of the acceleration vector parallel and perpendicular to the motion of the particle. But ignoring all these mathematical equations, what I really wanted to show, so I gave the equations here because to motivate what is being shown here. But what I really wanted to show was how this dipole pattern transforms as you transform to a different reference frame. So just before I showed that in a non-relativistic system, the emission occurs in a dipole patterns where if your line of sight is along the particle, you do not see anything. But if your line of sight is perpendicular to the motion of the particle, you see the maximum emission. Now, suppose this is what the emission is in the rest frame of the particle. Now, if you do a relativistic transformation, these lobes of the dipole will actually be beamed along the motion of the particle itself. And the center of this beam is 1 by gamma, has angle of 1 by gamma. Now, suppose the particle is the motion of the particle is perpendicular to the direction of the acceleration. So x prime, this arrow denotes the frame of reference or the motion of the frame of reference, let's say. And this A prime is the local acceleration vector. Now, the acceleration vector is perpendicular to the motion of the particle, which can happen, for example, if the particles are gyrating. So in that case, acceleration vector is perpendicular to the tangent of the velocity vector. Now, then this dipole pattern is again mapped in the forward direction into a small angle over here. And these are extremely important because this is the pattern that we will find is relevant for synchrotron emission. Synchrotron emission are relativistic particles gyrating very fast, rapidly along magnetic field lines. So magnetic field lines are longitudinal magnetic field line. And we know that particles will move or circle or make circles around the magnetic field lines. And if the particle velocities are very fast, then in the rest frame of the particle, you'll see an emission like this. But when you see from the lab frame, all of that will be beamed towards the instantaneous direction of the particle. And I will come back to this tomorrow when I briefly introduce synchrotron emission and the other emission mechanisms. So I will end my lecture here and I will take a couple of questions. And I guess all of you by now would have access to PB World's website. You will have the Q&A form. Please fill up the Q&A form with questions if you have. I will try to collect all of them together and answer in bulk when possible. So I'll take a couple of questions now. Sakshi Hegre.
Hello, sir.
Hello, Sakshi.
Hello, sir. Am I audible?
Yes, go on.
So I didn't understand that part, why we call stimulated emission as negative absorption, because when stimulated photon already stimulates the excited atom, so it releases one more photon. So why is it called negative absorption?
Negative absorption purely from a mathematical point of view. Okay, because look at it in this way. Absorption is you take away photons from an incident energy beam, right?
Yes, sir.
Emission is you add or contribute photon to the energy beam or the intensity beam. Now, if you have negative absorption, it's just the same as calling it as emission.
Okay, sir.
So when you place all of this in the radiative transfer equation, so if I just maybe go back to the radiative transfer equation, couple of slides back. Yeah, this part. Let's maybe this part. Yeah. So you can see the radiative transfer equation. The absorption term has a negative point here, a negative sign here, and it is proportional to the incident intensity. And then you have the emission term. So any change in emission or intensity in the beam will have a positive effect from the emission and a negative effect from the absorption. But the fact is the absorption term is proportional to the I nu. So the stimulated emission, the coefficient in front is the stimulated emission itself is proportional to I nu by this Einstein coefficient, that is P21. But so in terms of purely mathematical way, it is very similar to the term or the introduction of the term in the radiative transfer equation as we do for absorption. But this will have a plus B12 I nu somewhere here. So instead of having two separate terms with just proportional to I nu, we just collect all the constants in front and take a negative sign outside, which means it will be minus within bracket alpha nu minus the stimulated emission term. And since alpha nu minus stimulated emission, it's called a negative absorption. So it's just a mathematical way of how it is inserted into the radiative transfer equation.
Okay, sir. Thank you, sir.
Thank you, Sakshi. So next is Junik.
Hello, sir. Am I audible?
Yes.
Sir, my question is, when we are getting a spectrum and there are different kind of lines in the spectrum, how do we classify between which line spectrum, which line broadening is by quantum method or by collisional or by thermal methods? Between this?
We do it by fitting the line profile. So first of all, quantum mechanical transitions are not really relevant because they're extremely small. So in actual physical systems, what is relevant are the Doppler width, which is the thermal width, and the collisional width. Now, you can understand whether it is dominated by collisional width or the Doppler width by the nature of the line profile. If it's a Gaussian line, of course, it's just Doppler width, so there is no collisions taking place. If it's a Lorentzian profile, it's a collision, and that's why I said if it's a joint mix of both, we fit by the Voigt function, and the properties of the Voigt function will define, give you an inference of what is the dominant mechanism of the broadening.
Okay. Thank you, sir.
Okay. Sajna? Sajna K. Anand?
Am I audible, sir? Yes. Am I audible to you?
Yes, your voice is breaking, but let's try. Ask your question.
So what is the discrepancy between the power radiated and power lost due to radiation reaction for accelerated charged particles?
I am not able to hear you clearly. Sorry, your voice is breaking in between. Sajna, can you write your question in the Google form, and then I'll try to get back to you later, because we're running out of time. We have to prepare for the next question. Sorry about that.
Yes, thank you.
Sir, am I audible?
Yes.
Yes, sir. If you have defined as a one equation as in local thermal equilibrium, it is possible. But it was derived from statistical equilibrium, Maxwell-Boltzmann distribution,
yes,
which will not probably depend on thermal equilibrium, like canonical distribution.
Yes. So the true description of the Maxwell-Boltzmann equation, it does not define a thermal equilibrium, but if you have a temperature distribution, then you can consider the system to be in, a thermal system. So if you have a true Boltzmann distribution, it is just this G1, G2. Now this is how it looks like. But in local thermal equilibrium, this is how you get, where the energy states are defined by the temperatures of the system. So this is the definition that you get in local thermal equilibrium. And actually, I had used this over here. So up to here, we do not assume local thermal equilibrium. So we just keep them as a ratio of G1 and G2. But when you have a temperature of a system, that means it has temperature means it's in thermal equilibrium, and that's why we can use this system. Use this relation. Okay, Eshwaran, maybe okay. I can take two more questions.
Morning, sir.
Yes. Yes, Eshwaran, go on.
Sir, my question is: when we observe the spectrum of a star, whether there be a splitting in the spectrum due to the magnetic field of the star due to Zeeman effect, and if so, can we use the Zeeman splitting in the spectrum to predict about the magnetic field strength of the star?
Yes, you are right, and that can be done, and that is done. That is not really related to the topic we discussed here, but that is used, and you can look up papers on Zeeman splitting from OB stars or something. Okay, Anjali.
Sir, am I audible?
Yes.
Sir, my question was regarding the graph that you showed in the fields with moving charges. So can you explain the curved lines there? I understand that at x equals to 0, so it will be a completely radial field.
Okay. I see. When it stopped, yeah, this one.
Yes.
Yes.
So, see, sir, these curved lines which are connecting the x equals to 0 and x equals to 1. Can you just explain the significance of that? I didn't understand.
Right. So x equals to 0 is when the charge has come to a stop. Okay.
Yes, sir.
And x equals to 1 is when charge is actually moving from the right to the left. X equals to 1 is when the charge it was a previous location of the charge.
Yes, sir.
Okay, so the charge has started to decelerate from x equals to 1, and then it stops at x equals to 0. So all these vectors always point to the previous location of the charge, and this you can find out because of the way the direction of the vector will look like over here. Okay. It's r minus beta, which actually is also.
Sir, yes, sir. The straight lines I do understand. I do not understand why are these two lines joined by the curves.
So this is what the electromagnetic radiation would do, because at any point in location over here, before this information of the charge has come, it will keep pointing to the instantaneous location at x equals to 1,
okay,
which is the retarded location. But so the fact that the charge is stopped has not really reached, say, this point here. So at t equals to after a very long time, all of space would know that the charge, the electric field now would be radial. But at any given time, at t equals to 1, let's say, the field lines will just point towards x equals to 1, which was the retarded location of the charge. Again, this is a slightly counterintuitive concept to understand what is retarded position, retarded time, etc. But
sir, I got your point, sir.
So this is the information that is traveling. The fact that the nature of the electric field is changing, and this wave of information is the electromagnetic radiation.
So, sir, this curve will be there till the time CTR, the time that will take for the light to propagate from this to this place. Right. 1 to 0.
Yes.
Thank you, sir.
Okay. Last question, Vinay, very quick question.
Hello, sir. Good morning, sir. Am I audible to you?
Yes.
Sir, what is the difference between field produced by a charged particle and the radiation produced?
Radiation is electromagnetic fields. So any changes in the fields produced by charged particles, that is communicated as radiation. Radiation is nothing but the E cross B. So the change in the electromagnetic field structure due to motion of charges, that itself is radiation.
Okay, sir. Thank you, sir. Thank you.
Okay, so I'll stop the question answers today because we'll have to prepare for the next lecture. Please mute yourself if you have not. Let me prepare for next lecture. Thank you for listening, and I'll come back tomorrow and try to address the other queries you had, which you were not able to ask today. So thank you again. And Santosh, if you are here. Oh, there were some questions.
Yes, I'm here.
Okay, so just before I go to you, there are some two questions.
1 second, let me stop the streaming. Just
So just